I wanted to make a comment before we ask more questions. It's really amazing to see so many people involved in SYNGAP. I mean, when there were only 3 or 4 labs working on SYNGAP for many years, and now there's 20, 30. And so it's really incredible to see so many people contributing so much work. And I must say, SRF and other patient family groups have been really critical in spreading the word and also funding the work and bringing in people like Liz and people who weren't interested in SYNGAP into the fold and really advancing the field. So thank you, Mike, for wherever you are, and the other patient groups as well. So do we have questions?
Hi, Jack Parent from Michigan. This is for Dr. Till and Dr. Huganier. So the GAP domain knockout rat that had a phenotype, Dr. Huganier, I thought you made a GAP domain mouse that even the homozygous had barely a phenotype. Have you guys talked about what's going on?
Yeah, well, that's not published yet. I haven't talked about it. So we do have a.
Whoops.
So Sally and I have not talked about it, but we do have a point mutation in the GAP domain of a mouse, and our mouse is quite different. The expression of SYNGAP is full length. It has no GAP activity, and the heterozygotes are normal. They do not have the phenotypes that the heterozygote knockouts have, and in fact the homozygotes live, which is, as you've heard, most of the homozygotes die. So these homozygotes have no SYNGAP gap activity. And most of the behaviors are, so far, appear to be normal. So this suggests, at least in part, that we're not saying the gap activity is not important, but many of the phenotypes are mostly due to what we think is a structural role of SYNGAP and not to the gap activity. So we haven't really analyzed these mice in great detail, so I'm sure there's going to be phenotypes we just haven't found yet. But that's the result we're getting.
Yeah, and can you hear me? I can add to that. We have a colleague in Edinburgh who has made a point mutation in the GAP domain. And he finds that it lacks the enzymatic activity, and it's homozygous lethal, and heterozygous do show some of these phenotypes that are found in the SYNGAP heterozygous knockout mice. So it may have something to do with where exactly that mutation lies in terms of the function, and perhaps there's more than one function in this enzymatic domain.
Your mutant binds PSD95?
My mutant, yes, binds PSD95, yeah.
And as Sally very beautifully said about the difference between mice and rats, it could be a species differences too, as well.
All right, other questions?
Great session, everybody. Gavin, can you talk about the gains that you see in the various mouse models in terms of the floxed mouse, postnatal day 1 gets restored, and it's a normal mouse? What about the adult mouse, the floxed one that gets restored, compared to the change in the isoform balance? Are the gains similar? Is one much better than the other? How close to normal do they get? Can you give us a sense there?
Yeah. Is that Hans? Is that who it is? Yeah. So that's like a 6-pack of beer conversation, Hans. But I will try to briefly summarize. So, because I think it's an important point. So, initially, what Hans is referring to is back in 2014. Back in 2012, we published this critical period paper that emphasized that late gene therapy, like it's pretty easy to do gene therapy in mice because the tools are available. And late gene therapy didn't really have much of an effect on these very penetrant phenotypes that we all talk about. And that was biologically meaningful because it identified this period of time where SYNGAP is super active and does a lot of really important things for wiring the brain, which you talked about, right? Subsequently, now we know that it does more than just wiring the brain. So, we like to think about, because what we've done subsequently is looked really hard for phenotypes that are sensitive to improvement when you put the protein back in after development for obvious reasons. And those reasons have to do with, the community. So, and also I thought that if we could show evidence of adult improvement in animal models, that might also get more biopharma companies excited because you have a much larger patient base to work from, right? There's not some clock ticking, and that's for every single phenotype. And so that's actually what gave us the original reason to think about these different phenotypes, because we can get actually pretty important phenotypes to resolve when we put SYNGAP back in an adult. So I showed the example of the interictal spiking. Those exact same mice have improvements in long-term memory. This is memory where the information is transferred through the brain. It's thought to be kind of similar to the types of memories that humans form over a lifetime. And in the fact that a lot of the measures of epilepsy were improved, I thought were quite exciting because if it turned out to be a progressive disorder, I think that could be huge. So what I would say is that there are clearly developmental functions of SYNGAP. I think that everyone would agree with that, and that some of those could be difficult to resolve. But we don't know. But there are clearly functions that emerge in development but are used by the brain forever. And so that's why I said that neurons really want their SYNGAP back. So things like long-term potentiation, this ability for circuits to store information, that also was completely resolved in adulthood. That's why we think memory resolved. These brain oscillations, which shows the way that the brain triggers these, basically information processing in the brain. Those were also improved in adult animals, these theta rhythms. So, I'm quite optimistic that that you can get improvement outside of a critical window. I'm very optimistic in the Syngapians. The only other thing I'll say is that the isoform mice, if anyone's interested in how much SYNGAP you need to improve phenotypes, I'd look at this paper we just published this year. And I showed one slide, and it's okay. It's very clear to us. These Morris water maze, where the animal finds its way around, finds its way to a hidden platform using visual cues. It's a very sensitive task, and those animals that only have 20-30% of alpha 1 and alpha 2 upregulated has a very strong effect. And actually, my lab views SYNGAP1 as a drug target for common disorders. That's one of the reasons why I focus on SYNGAP1. Is I'm currently trying to make tools to upregulate different isoforms, as is Rick, but I'm going to use them in other common disorders like stroke and neurodegenerative disorders, because I feel like if we can show that will also get more people interested in SYNGAP in general, right? So that's the best I can do without any beer.
I just want to bring up another point, because there are papers coming out now that SYNGAP mutations affect very early development. There's a paper that's not published but on bioRxiv showing that radioglial cells very early are disrupted in their development. And this was a little scary because it means you have to treat prenatally if that's really going to be an important factor. But I think these things probably occur, but I'm encouraged that somehow the mouse at least can get through that period and still be rescued. And so that Gavin's work and some of our unpublished work is indicating even those early defects, even maybe the dendritic defects, the mouse can get through those periods of development and still be rescued by replacing SYNGAP later. So just don't get too worried dismayed by these studies is my message. But all right, Other questions? Back there.
Now that you bring up, I think it's Giorgio Quadrato's paper with the organoids, that the Zhang lab in Chicago doesn't think there's any productive splice variants in the neural stem cells, and is skeptical, and I wonder if you guys have looked early for expression.
Yeah, so I can say that there is expression in, well, I don't know about the stem cells. There's no, in iPSCs, we see nothing, for sure. But even tissues, there's a lot of unpublished data that I know of, so I have to be careful. So tissues where you may look in a database or even do a Western blot in your own lab and don't see much SYNGAP there, there's pretty clear evidence deriving from stem cells, iPSCs, that those non-neuronal cells are actually really important. One of them would be blood-brain barrier, neuroepithelial cells. Very little SYNGAP protein in there, but there is protein, and it looks like that protein actually is very important. So, I don't know. I mean, there's protein in HEX cells, but there's not a lot of it. But I mean, we don't know if it's functional or not.
Yeah, a little protein could go a long way. So,
For sure.
all right. Any other questions? All right. Great. So we're 10 minutes early.
That's amazing. Because I just wanted to make, Liz, do you want to say something? You just grabbed your mic. Dr. Heller?
I'm turning it off.
Okay.
Sorry.
I made it. I just want to make 2 quick points. The first is, if you're a family member in here and you've got a splitting headache, you're not alone. This is why we have the family day tomorrow. I think part of the point of having the families in the room for the science day was to help you understand how incredibly complicated this is, to appreciate how important it is that we continue to support this work. Because Gavin, Dr. Rumbaugh, Dr. Till, Dr. Heller, Dr. Huganier, these guys are on the cutting edge, and they're thinking about incredibly complicated problems, and what they are learning in their lab will help us make more sophisticated solutions. And I welcome differing opinions from the geniuses before us, but just because we do not fully understand every single thing that SYNGAP does, this is an important point, does not mean that the ASOs that Stoke and Praxis and others are working on could not help our kids before we fully understand what SYNGAP does, right? And maybe, now that I've introduced this new idea, I'll throw it back to the doctors before us to explain this better, but there's a bunch of regulatory mechanisms, whereas if we just use what Dr. Collar talked about or someone's ASO, the body could solve that problem just by making more SYNGAP and let SYNGAP deal with its own complexity. So we shouldn't be overwhelmed by the complexity. We should be grateful that there are people like this working on it, and there's also people like Praxis, Stoke, et cetera, working on therapies. And the next session, this is actually a commercial for the next session, is about how will we create that clinical trial. So thank you to my points are, thank you to the panel, take a 5-minute break, unless somebody wants to comment on
Mike,
what
can
I
I
just said.
just say something? I
Yeah.
mean, I think the key is that we don't really even need to know what SYNGAP does, right? So at this point, it's good we do, but I think the bottom line is we need more SYNGAP, and I think that's what I think is easier to understand. And I think the interest, it's not just Praxis and Stoke. There are at least 10 different companies starting SYNGAP programs. So, these people are smart. They're not doing this to lose money. So they think there's a possibility for treating the kids. So there's definitely hope.
So I would just say I agree. We don't know how it's going to work. We just don't know. And so I doubt, even if so I'm optimistic ASOs will work, but just like any drug, I doubt it's going to work the same for every kid, right? I mean, just look at, anti-epileptics or, neuroleptics. Certain patients respond better than others, and we don't know why. And so we need a shelf of treatments to pull from. I think someone said it earlier today. We need different types of medications for even for rare disorders. I think that's the idea. And so the more we learn, ASOs is our foot in the door. That's absolutely the quickest way to a drug. I think everyone will agree on that. But what do we do for the next generation of drugs? And that's where biology and animal models and CRISPR tools and human-derived neurons, I think, is it's going to help us with the next generation of therapies.
Agree, Gavin. I would add to that. I think we could imagine a speed dating round between session 1 and session 3, right, where we talk about which of the techniques we talked about could potentially be trialed in which of those models. And it is because you're getting into the complexities of the mechanisms that maybe we can go deeper. So maybe we can have that happen during our breakout sessions. But thank you so much for sharing all of your data, published and unpublished.
You want to talk about the next session?
We can talk about the next session. After a 5-minute break, we're going to regroup and hear from Dr. French and Dr. Moore, and then we're going to be sending you all to breakout sessions. Kim's going to put up some questions. You can self-aggregate according to which question you'd like to discuss, and we'll find some spots for everyone to meet, and then we'll come back and have a group discussion.